Bir doktor metodunda projemiz var. ETV'nin projesi. Bu projemizde toplamda 7 ülke olarak çalışıyoruz. 19 rehber öğretmeniz. Amacımız uzaktan eğitim sürecini değerlendirerek güzel bir matematik kitabı oluşturmak, etkileşimli bir matematik kitabı oluşturmak. Bu süreçte de farklı etkinlikler yapabilir miyiz diye düşündük. Bir anket yaptık grup arkadaşlarımızla ve bir matematik uzmanından seminer almak istediler grup olarak. Biz de İpek hocamıza başvurduk. Sağ olsun onlar bizi kırmadı ve şu anda inşallah güzel bir seminer dinleyeceğiz ondan. Zehra hocam çevirebilirsin.
Tabii ki. Hello dear friends, welcome to the meeting. Now our host, co-host is İpek Saralar-Aras, and she will give us a seminar about the project that we are going to talk about. She will introduce herself, and the aim of the project is to create a mathematic material book, an e-book. We have 19 partners in this project, and I'm from Batman. Now, İpek Saralar teacher will introduce herself.
Well, we have our scientists coordinator, Dr. Tunç Erdal with us. So after his introduction, I'm going to start my presentation. So it's your turn to talk about Tunç hocam.
Okay.
Thank you very much, İpek hocam. I am the scientist coordinator, scientist project coordinator in Turkey, national contact point. Today I will introduce now Dr. İpek Saralar-Aras will start to her presentation. Before the presentation, let me introduce her to you. İpek Saralar-Aras is a graduate of Middle East Technical University, bachelor and master's mathematics education degrees, have these degrees. Mm-hmm. She completed her second master's degree in educational technologies in England. In the meantime, she started working as a research assistant at the University of Nottingham and continued her job until she completed her doctorate education. İpek completed her doctorate in the field of technology use in mathematics education in England. Currently, she is working as a national education expert in the Directorate General of Innovation and Educational Technologies of the Ministry of National Education in Turkey. Floor is yours, İpek hocam.
Thank you, Tunç hocam. Hello, everyone. Let me first share my screen with you. Start sharing. Here is the presentation. Start from beginning. So I just want to talk about how we started to do this presentation. So one day I received a message from Gamze Öztürk saying, well, we have an idea, we have a project, and in collaboration with this project, is it possible for you to give a seminar or webinar for our, not only for our community, but also available publicly for all teachers. And I contacted with our scientist coordinator, because when it comes to mathematics, scientists is quite related. And the scientist coordinator, Tunç Erdal, welcomed us. And now, through the scientists project, in collaboration with Dr. Matt, I'm going to give this presentation to you. So it's about maths education in England and the research, obviously, and adaptations for Turkey. So Tunç already talked about who I am and what I studied. So it's going to be a very brief introduction about my education. So I graduated from the Middle East Technical University. I have maths education, bachelor and master's degrees from the university. Then I went to England and I have educational technology degree in learning technology and education from University of Nottingham. And at the same university, I also got my master's, my PhD degree, which combines both of my masters. So both in maths education and educational technology. So my PhD focused more on technology integration to maths education. And today what I'm going to talk about is mainly the doctorate project that I have. Not probably all of it, but some part of it. So the aim of my project was inspiring from the mass education from the United Kingdom and the research that I read all over the world. I tried to facilitate secondary school students' learning of three-dimensional shapes. And for this, I designed lesson plans, and all lesson plans will be available for you if you email me, and I'm going to give my contact information at the end. So I designed these lesson plans based on what I learned from the literature, and then I went to schools in Turkey to implement all these lessons, evaluated my lesson plans, because not everything we plan is working in the classes. All teachers know. Then I improved the lesson plans, and I went to schools again, and I iterated these four times. When I say 3D shapes, what I mean is polycubes or polycubical shapes. And I specifically focused on specific 2D representations of them. So one of the representations were elevations. So that was the different views of shapes. So students are provided with the shape itself, and they're asked to draw front, left, right view. So different views of the given shape. And in another part, I also asked students to make isometric drawings. So I gave students the front, right, top, back, left views, and I asked students to draw 3D-like shapes. And you may ask why I was interested in this topic and why it's important at all. So there's a little bit background. So I'm not going to bore you with the theoretical background, but I have a PhD on it. So there's a huge literature. We know from the literature that secondary school students have difficulty in representing three-dimensional shapes in two dimension. It's been ages that is stated. So from the early 90s and late 90s, even the 80s. So it has always been stated that students have these difficulty. Even in 2017, Fujita and colleagues published an article saying, well, there is still this difficulty. And in 2020, I myself published an article and said that the case in Turkey is not different than what you've already mentioned. So there is still this difficulty. So my research focuses on the intersection between spatial thinking and geometry. So I devoted my time to increase geometric spatial ability. And when I say spatial thinking, people think that, well, males are already better than females, and aren't they? So I don't think so. Males can be better at some spatial abilities, but females can be better at some other spatial abilities. For example, I think of myself looking for my notebook when I was a child, and I was not asking for my dad to find it. I was asking to my mom about finding it. So why not that? Because mom knows the place of everything, and that was about spatial thinking. So even from my child mind, I knew that there's something about it. So I designed a geometry test, and this geometry test was based on past ministry exam questions in Turkey. So in the ministry exam, students mostly are provided with a shape, and they are asked to choose one of the options showing the correct views. For example, the correct front view, correct top view, and correct views. So in the first part of my exam, I asked such questions. And in the second part, I again provided students with the shapes, views, for example, front view, left view, all these views. And I asked students to draw the isometric, so make the isometric drawing themselves. And there can be many answers, many possible answers to that, thinking of the perspective of it. So I accepted every possible answer. That's why there's an or in between these shapes. So let's start to my first study. So before investigating what's happening in England and how English people teach it or what the research say, I decided to come to Turkey and to see what's missing in Turkey and how can I improve the Turkish education system, thinking of what I learned from England and the research that I read in England. So first I went into the schools and I observed 4 teachers, so 4 different classes for about 4 weeks. And before and after these weeks, obviously, I was in the classes, so I interviewed teachers about what they think, and after the lessons, I also interviewed both teachers and students about their opinions and whether they found the topic difficult or whether they found it easy and all the stuff. And what I found, so what was currently happening at the time I was doing this research. What I found was, well, the practices in Turkey was mostly teacher-centered. So how was the case in Turkey and what was currently happening? So the teaching was mostly teacher-centered. Specifically, experienced teachers were not giving students enough chance to express themselves. And although there were Fatih project and students are mostly provided with tablets or classes are provided with smartboards, teachers was not really using the smartness of the smartboard. So when we think of it, while drawing all these shapes, rather than opening a software like GeoGebra or Cabri or any other software, teachers were drawing the shape themselves as if they're using a blackboard. So yes, they're drawing the correct shapes and there was nothing wrong with it. But why not using the technology if we have it? And another point that I found was exam-focused instruction. So almost all of the teachers I observed use ministry exam questions, either ministry exam questions or mention during the class that there will be an exam in the end. So the motivation point was there will be an exam, so you have to learn it. But is that really should be the main focus? So there is an exam, so after exam I can forget what I learned about all these 3D shapes. So no, that was not the point. So we needed to change it somehow. And when I go back to England, I decided to find out how they solve this and what they do about it. I also reported some difficulties in learning about 3D shapes. For example, instead of combining given elevations in one shape, some students draw separate shapes for each of the view. And one of them said, you know, for me, all orthogonal views separately create their own shapes. Really? So we need to change it somehow. Another thing I found was representation errors. So one of the students imagined the shape correctly in her mind, but when it comes to drawing it, she drew the shape inclined. So the shape would be correct, but it was missing a cube as well as it was inclined. So that wasn't even how students need to use isometric paper. And I also wanted to see what is the outcome of this teaching. So out of 20 points, in orthogonal drawings, the students need to draw separate views, such as front view, left view. Students, on the average, got about 12 points out of 20. So they answered more than half of the questions. Still not good enough, but more than half. And when it comes to isometric drawing, students answered almost 5 of the 20 questions. So when it comes to that, students got only a quarter of the knowledge or skills that they are required to have. But there was something missing. And also question type was important in this. So students found isometric drawing harder than orthogonal drawing, as well as students already have difficulty in orthogonal drawing anyway. So what I did. So how I bring my experience in England to Turkey to improve our teaching. So I designed a model. I called it Rita, and it has 4 design principles: realistic, exploratory, technology enhanced, and active. And with the realistic, I tried to integrate real-life examples to lessons. I was working as a research assistant in one of the projects in England, so realistic maths education. And in this project, I found out that, well, there was real-life examples they're integrating, and students are not learning for the sake of learning. They're learning to use the information in their real life. So why not? We can do this. So I decided to integrate that. Exploratory, where students explore the design mistakes. Technology enhanced, where I integrated technology to lesson so that I can facilitate students' learning. And active lessons, where students themselves can build all these shapes using concrete manipulatives as well as technology. So I'm going to explain each of these principles one by one. So realistic example intend to integrate real-life examples and context into lessons. So what contents are they? For example, while teaching this specific topic, I integrated examples from engineering and architecture. I integrated the video from engineering and a photo from architecture, and I asked students to discuss whether these jobs really need to do these drawings. And they were aware that, yes, if they want to be one of these, if they want to choose one of these careers, they will need to use these drawings. So they need to learn them for themselves, not for passing the exam, for example. And after that, so these were more complicated than students are supposed to do. Therefore, after these, I introduced all the shapes that they need to draw, and they draw multi-views themselves. In this way, I provided concrete examples, real-world applications of the knowledge and skills they needed to learn. I also chose GeoGebra, but before passing to GeoGebra, I introduced CAT, which is more complicated than GeoGebra, but actually has a real-life use. So students learned about CAT and then started using GeoGebra, saying, oh, this is these are very alike. In this way, they can not only do make inferences about real-life relations, but also these improve their understanding in the end anyway, also increase their motivation. And the second principle is exploratory, where I use worked examples. And if you're not familiar with worked examples, the ones that I chose were design mistakes. So in the first study, I found commonly made mistakes by students. Then with the exploratory example, while I was designing my lessons, I integrated these examples to my lesson plans. And I gave these mistakes to students, and I asked them to find why these are wrong and then make the correct drawing. The exploratory principle also asked them to explore real-life mistakes. So each principle were already related with each other. So there can be mistakes in drawing, and there can be mistakes in real life as well. So things can be built very short or very long, or intersect, and there can be all these things. And I specifically like the example that I highlighted now. Even though 2D representation is correct, while trying to change it, transform it into real life, there can be some mistakes. And this isn't about the drawing itself, it's also about the interpretation. So students then in this way, after exploring all these examples, learned they really need to interpret. And the third principle is technology enhanced. So technology can be any technology. And for this specific topic, I use dynamic geometry tools. What and why? So in my MA dissertation, I interviewed teachers and found out that Turkish teachers had already a positive attitude toward GeoGebra, but their use was limited with some topics and with the challenging parts of the topic. For example, it was quite common to represent these slightly simpler shapes with GeoGebra, but when it comes to harder ones like this, it was first challenging to use GeoGebra. Second, teachers found it time-consuming to use GeoGebra. So I decided to integrate first concrete examples. So students are provided, in the lesson plan, students are provided with the shapes themselves, like a castle. And then they build the shape using concrete manipulatives. And after the concreteness, they transformed the shape they constructed to GeoGebra. And in order to find the different views, I call them orthogonal views. For example, for the front view, they just rotated the shape itself because GeoGebra allows it to do. And after the rotation, they found the front view. And after that, they draw the front view to their worksheets. And we are coming to the final principle, which is active. So I decided to make students active because in most of the lessons in Turkey, most of the observed lessons in Turkey, obviously there are many other teachers who are actively engaging their students. In the lessons I observed was students are mostly passive and learning passively somehow. So, and what I try to do is creating active learning environments where students themselves have the control of tools and manipulatives. And how can I make students active? Actually, making students themselves control the tools and manipulatives. So these are some of the screenshots from a case in Turkey. Teacher, in this case, for example, doing the fun part. So they're big unit cubes and they're on the teacher's desk. And either teacher or one of the students is constructing the shape. But what about other students? They are mostly passive. So what I decided to do was giving this smaller version of unit cubes to students and making students active. In this way, I also found out that for the same school shape or for the same castle, there were very different constructions. So students imagine, visualize all these shapes differently, and their drawings or constructions can be correct, and we need to learn from them. But if we don't allow them to create all these shapes or build all these shapes, then we can't know what they imagine, and we can't know why they're drawing incorrectly. So after all these constructions, I again assigned different students to different groups. For example, there were different shapes and different colors. One of them was dark blue, and one of the students drew the shape. And I gave some examples. I'm giving some examples to you here. So students constructed the shape, even the difficult ones, with many unit cubes, and they saved their files and shared with me. So I had a chance to control and to see whether they're actually doing correctly or whether they're using GeoGebra in an ineffective way. And there were discussions. In math lessons, in most of the math lessons, what's missing is discussion. Students are not discussing what they do. They are writing the problem, they're solving the problem. What about discussing about the problem itself? So after building this shape, for example, for the same school building, two students draw two different concrete shapes. And Then they discussed with each other, and each of them explained their visualization and construction to each other. And there was nothing wrong with the thinking. So this gave them chance to actually express themselves in mathematics, to discuss what they think. Again, after finding the mistakes and explaining why, they had a chance to discuss. And I really like this example. They had also a chance to discuss all these real life examples, and they had fun. So, after designing all these lessons, I decided to go into school. But changing the lesson plan, taking almost 4 weeks of lessons, that was quite hard. So I decided to make the first trial of my lessons as an after-school class. So I went to school, and some 8 students have volunteered for my lessons. 8 students volunteered for extra mathematics lessons, and that was an important thing. So, and I decided to see how they see my lessons. So I was in the class, I was teaching, and I tried to see how my students experience all these lessons. There were obviously both positive and negative experiences. So there were real life examples that I found, and students liked the real life examples. They wanted to watch the video again, for example, but when it comes to discussing them, they found it quite challenging. And I added extra discussion questions to these activities for the next iteration. Students again quite like finding the mistakes, but when it comes to discussing why someone can make these mistakes, they found it quite hard. They found it hard to find the mathematical language. They also find it quite hard to put themselves into somebody else's food and try to understand why somebody can make this mistake. And technology. So I just thought that these students are technology native themselves, so they can explore GeoGebra in the given time and they can use it easily. But that wasn't the case. Even those students needed to explore GeoGebra with a structured, specifically designed activity. So I added this activity for the next iteration. And finally, in the active part, students really like being active and they constructed very different shapes. So they explained this part mostly positively. So what were the outcomes? So I found many outcomes, but outcomes about the realistic principle were quite observable. So before the lessons, when I interviewed one of the students, he said to my question about real life use of 3D geometry, I asked whether we use 3D geometry in real life. And the student said, I think yes, of course. Because in my mind, he's thinking that, well, I am coming from the ministry and I'm asking as a teacher whether this is needed in real life, whether this is important. And the answer was, I think yes, of course. But when I asked further question about, can you give me an example of it? Well, the answer was, well, I don't know. So they didn't really know about the real life use of all the topics they're learning about 3D geometry. But after the lessons, when I asked the same student about the question, about the same questions, what I got was quite interesting. So the answer was, 3D geometry reminds me of drawing mistakes of architects and engineers and their consequences in the photos. And I added, because I showed the photos themselves. And the student himself described it as exciting and fun to discuss mistakes in real life. So I had 8 students, and I couldn't do any statistical tests for this specific study, but it was observable that there was an improvement. First of all, I want to say that these are volunteer students for extra math classes, so they were already good at maths. In orthogonal drawing, before the intervention, they got about 17 points out of 20. And after the intervention, except one of the students' mistake in only one of the questions, all of the students answered the questions. So they come to the point that ministry want them to do. In isometric drawing, this was more observable. So they started by getting only half of the questions correctly, so about 10 points. And after the intervention, they got about 17 points. So there was quite improvement. So what I did next, I went to my next study. So I improved my lessons as I explained. And then instead of me going into class and teach, I asked one of my colleagues to teach my lessons. So I collaborated with a teacher. She was quite experienced. She had about 30 students in the class, in almost all the classes. And this time, instead of reporting how students feel about it, I reported how a teacher feel about it. Because the examples, the things that I asked as extra, so finding videos, finding technology to use, all these were extra work for the teacher. So there were some opportunities and challenges for the teacher. About realistic principle, teacher mostly feel positive about it. So at the beginning, before the lesson, teacher said, well, students always ask whether we are going to use the mathematics in real life, whether we are going to need this mathematics in real life. And teacher said, well, your lesson plans will be my answers to that. But when it comes to the lesson, instead of giving students a chance to discuss, teacher decided to explain the real life examples. So teacher showed the video and explained how, for example, engineers use these drawings in real life, but teachers didn't give the chance to students to discuss whether they really think that they're going to be useful. About exploratory principle, well, this was the most positive experience of teacher because I was giving some problems and teacher could easily see how students perform. So this was very similar to how she could already do, except for there was an additional incorrect answers that then they need to change. So if we just eliminate the wrong answer that I'm providing, this is quite like how she would supposed to teach it. So how she would teach it herself. And when it comes to technology, well, teacher experienced technology very, I don't want to say negatively, but she was quite far from it. So she said she didn't use GeoGebra before. She was not teaching with technology, and she was about 20 to 22 years experienced math teacher. And it was quite hard to change her teaching and introduce herself something else. And when it comes to the lessons, so the teacher opened GeoGebra, so I was lucky. So she didn't eliminate it from the lessons because I gave teacher the agency to change lessons and adapt for her own use. But students themselves discover GeoGebra rather than teacher teach them how to use it. And thanks to the activity sheets that I planned with my experience from the earlier cycle, that students followed the activity sheet step by step to discover GeoGebra. So it didn't take too much time for students to discover it. And finally, the active principle. So when we think of the profile of experienced but not quite open teachers, because some experienced teachers are quite good at using technology, so I'm not just generalizing them. This teacher said to me that the discussion parts of my lesson plans made even the most silent students noisy. And well, this was what I wanted to do. I wanted them to discuss mathematics but the teacher was quite traditional, let me say, and she wanted the pure silence in the class while she was teaching, rather than students discuss something. So that was her experience about it. Even though all the challenges we faced, still there was something we found, that in orthogonal drawing, students started at about 15 points and come to the point that where they got all the points. So they got 20 out of 20. So when we think of it, so if all students answered all the questions, then the questions were easy, or they're not measuring what they're supposed to measure. But the difficulty of the questions were in the same level of what Ministry wants students to be at. So this means students come to the point that the Ministry wants them to be at. So that was quite fun. And in the isometric drawing, the case was more or less similar. So they started at lower levels, like 8.7, 9.3, and they come to the point that they got 18 or 17 out of 20 questions. So they improved themselves. So far, I said that, well, the lesson plans are working, students are improving themselves, but are they improving themselves more than how teachers already teach? So if my lessons are only good enough for the traditional lessons, why would teachers use them? So I decided to see, so that was the very end of my PhD, and I decided to see whether my lessons are better than the traditional lessons. And I was so nervous because I have spent 3 years of my time to improve these lessons, and if the lessons were not good enough, and if the lessons are only good enough for the traditional lessons, then I probably missed 3 years of my time. So I went into lessons and I collaborated with teachers, and these teachers volunteered to be in the traditional, volunteered to use their traditional lessons, or volunteered to use my lessons. And what I found. So I found an improvement, but this table is quite complex and full of numbers. So after the presentation, if you email me using my contact information I'm going to give at the end, I'm going to share this with you, and you can look further at the statistic that I have. But I'm going to show you a simpler version of the findings. So the intervention group used my lessons, and the control group continued using their own lessons. And in the orthogonal drawing, the students in the intervention group improved 7 to 7.5 points. The control group also improved, but the improvement was about 2 points, 2 and 2.5. So there was about 5-point difference. So my lessons were better thinking of this 5-point difference. But when it comes to isometric drawing, the difference was bigger. So the control group, where the traditional lessons used, students, specifically female students, for example, improved only 1 point out of 20. But in the intervention group, students improved almost 11 points. So I'm not saying the traditional lessons are all ineffective. I'm saying the RITA model, the lessons designed with the RITA model were more helpful and improving students more. So there was a difference between the improvement scores, and I could easily say that the RITA lessons were more effective. So what I'm saying that secondary school students have difficulty in learning 2D representations of 3D shapes, and realistic, exploratory, technology-enhanced and active lessons are promising to help these students learn. And RITA lessons and the lessons designed with RITA were able to provide new learning on 3D shapes and even more than the traditional methods. So why not using them? So if you're a teacher, math teacher, listening to this presentation and attending to this webinar, and if you're interested in using the lesson plan that I designed, I'm happy to send all these lesson plans to you because I want them to be useful. I designed them, but I'm a researcher, I'm a national education expert, so I'm, as a background, I'm a teacher, but I'm not actually in the class teaching, so I want to give all these lesson plans to you teachers to use them. Or, you may not use them as they are, so you can adapt them for your lessons. So they're already prepared, so you don't need to prepare them. So here are the, so we are coming to the point where I'm about to stop. So if you say, well, I am a teacher, but I may not use all these lessons, but I'm interested in the model. So could you tell me more about the model itself, or could you give information about the model, or whether the model can be used in other lessons than mathematics? So I'm also happy to send Vita model related information, my publications, and my, for example, conference proceedings, articles to you, so that you can read and see whether you want to use it or you can adapt your lessons with the Vita model. So we came to the last point. Thanks again for inviting me, Dr. Project. And also thank you, Tunç Hocam, for giving us a chance to give this webinar to scientists. Here are my email addresses. So I have two email addresses. One is my personal one. One is the institutional one. I'm using both of them actively. So if you want to send me anything, you can use them. So again, this is Dr. İpek Saralar-Aras, and we came to the last point. So I will say thank you again. And if you have any questions, I'm happy to answer.
Thank you very much for your presentation. Gamze teacher, do you have anything to say? We can go back to the Turkish if you want.
Teşekkür ederiz İpek Hocam. Gayet faydalı bir seminer oldu bizim için.